Okay? So, as you were saying, in general, if you've got a pair of sets and you know something about them, you may ask, is there a function from x to y with a certain property? Like, you could ask, is there a, if you're looking at cardinality and so on, is there a bijection between x and y? Things like that would be a question about cardinality. So you know there are lots of questions you can ask about functions. Well, so let me give you one of the many versions of the axiom of choice. There's lots of different ways of doing this. So suppose that S is a non-empty collection of non-empty subsets of a non-empty set X. Okay, so what's going on here? So you've got a non-empty set X, and you've got a collection of non-empty sets in here. So S then is a subset of P of X. Okay, because S is a collection of subsets of X. By the way, that means, for interest only, S is an element of P of X. If you're a subset of the power set, that makes you an element of the power set of the power set. Now, a choice function for such a collection a function f from S goes to, well, I'll say it goes to X here. I mean, you should go to the union of the sets in S. But so I may as well say it's going to X. And with the additional property for each E in S, so if E is in S, that will mean E is one of these non-empty subsets of X. F of E, which would be an element of X, it shouldn't just be any odd element of X, it must be in the set E. Now, I think a specific example might be helpful here. So the idea is that this function f is choosing one element from each E in your collection. You often do this for S being the whole power set, but when you're doing the Zorn's lemma bit, it's quite good to be able to do this for any collection of non-empty sets, and then to be able to build it up by adding in another one. So let's have a concrete example in a less interesting setting. So, for example, we could have X equals the natural numbers, and S could just be a collection of non-empty subsets of natural numbers. So it's going to have a few sets here. Let's have 1, 2, 4. Let's allow a bit of overlap. 1, 4, 5. That will do, okay? So S has got 3 elements. Let's call this E1, E2, E3, where of course let me say E1 is the first set, E2 is the second set, E3 is the third set here. So a choice function for S. Hey, this is great because this is going to answer both of your questions at the same time with a concrete example, and that's the best thing you can possibly do. A choice function for S is, remember, it's a function f from s goes to x, though really, morally speaking, I should take it to the union of the elements of s, but it makes no difference really here. But just to give, let's, but such that f of E is in E for all E in S. So we need f of E1 is an element of E1, f of E2 is an element of E2, and f of E3 is an element of E3. And that's all we need. And now you can immediately see that there are lots of choices. Actually, because there's only one element in E1, there's no choice about f of E1. F of E1 has to be 1. But there are 2 choices for f of E2 and 3 choices for f of E3. So how many possible choice functions are there? 6, that's right. There are exactly 6 possible choice functions here. So what does the active choice say? It says, if you've got some non-empty sets, choose one element from each set, and then you can define a function which picks out that element from each set. And that's a choice function. Obviously, if the sets have got more than one element in, then you expect that you've got lots of choice in your choice function. There may well be infinitely many sets, and so on. So now, as a slight more challenge, suppose S is as big as it could possibly be here. Suppose S is equal to all sets E contained in the natural numbers such that E is non-empty. Which is, of course, equal to the power set of the natural numbers, except you mustn't have the empty set. Of course, you can't choose an element of the empty set. So the most you could hope for is to choose one element from each non-empty set. So we don't allow the empty set. Now, the axiom of choice says that there is a choice function that assigns to every non-empty element, every non-empty subset of natural numbers, an element. But fortunately, in this particular case, we can actually give a specific example of a choice function. So this is one setting where you can actually give an explicit definition of your choice function and therefore see that the choice function exists. Does anybody know? Who can suggest what my choice function could be with an explicit definition here? Yeah. The natural numbers is well ordered. Every non-empty collection of natural numbers has a least element. So we can always take the least element and that actually picks out. So we can explicitly define a choice function here. F of E equals minimum element in E. Note that the natural numbers is well ordered. With its usual ordering. So we know that every non-empty collection of natural numbers has a minimum element. And we can take that minimum element and call it f of e, and that gives you a choice function, an explicitly defined one. Now, suppose you were working with the rationals instead, or say you're working with the positive rationals. Well, they're not well ordered with the usual order. So how could you, suppose you wanted an explicit choice function that picked out some element of subsets of the rationals, non-empty subsets of the rationals, or non-empty subsets of the positive rationals, or something like that. You haven't got your standard order of the rationals won't help you. You can't take, even if you're working with the positive rationals, you don't expect to be able to find a minimum element of a non-empty collection of positive rationals. Any suggestions as to what you might do if you're working with the rationals instead?
Is there some kind of theorem which states that there is an integer next to each rational?
So
You could use always that theorem to get some kind of ordering for rationals.
okay, so you could try to order the rationals, but what would you do with, say, a half, a quarter, and a third? Would you use the usual order of those?
Half, quarter, and third.
I mean, of course, you go to the nearest integer, then all end up at the same place.
Yeah, that's true.
Well, okay, maybe a half would round up, but at least a quarter and a third would both end up going to 0. And so going to the nearest integer might not be definitive. It might, in fact, lose you some of the information about the rational number. So I'm not sure if that one would do it. And they are ordered, but they're not well ordered. A well ordering is a special kind of order where every non-empty collection has a minimum element. Yes?
So you have a bijection between the rationals and the natural numbers.
Okay, so, yep. Yeah. So we know the rationals are countable. So if you choose some specific bijection, so you can actually make it pretty concrete. You can find a reasonably specific bijection between the rational numbers and the natural numbers, varying degrees of concreteness. But suppose you've chosen one. Oops. So note that Q is totally ordered, but not well ordered with the usual order. Is everyone happy about the difference between a total order and a well order, or anybody want me to say more about that? We're sort of seeing a specific example here. We know that the rational numbers are totally ordered, but for a well order, every non-empty subset should have a minimum element. That's not true for rational numbers, because you could say, take the strictly positive rational numbers, and then it's got a greatest lower bound of 0, but there's no minimum strictly positive rational number. So it's not well ordered. Also, it's also not bounded below, which is another problem. I mean, that would show that even the positive rationals are not well ordered. Notice that the integers is not well ordered because it's not bounded below. So, for example, there's no minimum integer. It's going to the positive integers on natural numbers, and bringing in a bound below is what gets you to the well ordering. So if you use the whole of the integers, that wouldn't be a well ordered set anymore with the usual ordering. Okay, but what you could do, you've got any countable set if you found some bijection between these natural numbers, so an infinite countable set. So we can find fairly concrete, if you want to try and find one, concrete bijection from, let's call it G, from Q goes to the natural numbers. And you can use G to transfer the order from the natural numbers to Q to get a new order. To give a new order on Q. Can everyone see how that transfer would go? I could write it down in one line, but I think it's fairly clear. When you've got bijections, you can pull topologies around, you can pull metrics around, you can pull orderings around, and so on, in the sort of obvious way. Does anyone want me to say more about that? Okay, so let's assume that you're happy with that. I could write it down, but when you do that, this makes Q into a well-ordered set. It's a well-ordering on Q. And now you can define an explicit choice function in terms of that well-ordering. For non-empty subsets of Q, in terms of this well-ordering. It's the same as before. You've got an ordering, it's a well-ordering, every non-empty collection has a minimum element, and you can choose that element, and that can be what your function does. Does anyone need me to say any more about that? Okay? So these are relatively concrete examples of choice functions. For the natural numbers, it's incredibly concrete. For other countable sets, you would usually go via making them well-ordered in some way. And then, of course, you take any odd set. The well-ordering principle tells you that it can be well-ordered, and then that gives you choice functions. But, and so on. So if you accept the well-ordering principle, then you get choice functions from that. This is how you could easily see a lot of these things imply each other. The Zorn's lemma implies the well-ordering principle is actually quite hard, relatively hard. Of all the Zorn's lemma is normally quite good at implying things, but Zorn's lemma implying the well-ordering principle is one of the harder ones. It's on the question sheet with a solution, I believe. So you can see how it works. But it's surprisingly subtle. Do people feel that they know what a choice function is now? And you've seen some specific examples. Good. Do you see why most people feel that the axiom of choice is right? Because all you have to do is choose one element from each set, and then you've found a function. And that's why most people think it's true. But you know, how can it not be true? They're non-empty, so you can choose an element from each. But when you see all the things that you can deduce from it, you start to wonder. Especially things like the Banach-Tarski paradox, which is, you know the Banach-Tarski paradox? Banach-Tarski paradox says that you can, if you take for example, a solid closed ball in three-dimensional space, you can cut it up into 5 disjoint pieces, rotate them, translate them, and put them back together, and then get exactly 2 copies of the original solid ball. No overlaps and nothing missing. And that sounds impossible, but actually it's not a paradox. What it proves is that the pieces you have to cut it into, using the axiom of choice, are so complicated they can't be assigned a volume. And once you chop things up into sets which can't be given a volume, all bets are off. And the same thing goes for chopping up a P into finite many pieces and rearranging the pieces back to give you something the size of the sun. Of course, you need quite a large number of finite pieces at that time. You can't do it with 5 by a simple argument involving diameter. And so what's the conclusion from that? Those pieces that are so complicated they can't be assigned a volume are clearly nothing that you're ever going to meet in real life. And again, makes you suspect that the axiom of choice is too good to be true. But we will be using Zorn's lemma and the axiom of choice in this module. And anybody who wants to know which results remain true without it, I'll do my best. Actually, I'll do my best as we go to say, well, actually, if you don't have the axiom of choice, this one might not quite be true. For example, Tikhonov's theorem is not equivalent. Let's get this right. Tikhonov's theorem is not equivalent to the axiom of choice, but the non-emptiness of infinite products is, if I remember correctly. So the axiom of choice is exactly the same as any infinite product of non-empty topological spaces must be non-empty. You need to be able to pick out at least one element from each of the sets you're taking the product of, you see. And that's just like the axiom of choice. I'm not a set theory and logic person. In fact, this whole area is so fraught, the foundations of maths are such a problem that there's a whole theory devoted to it, and there's Gödel stuff showing you that you cannot prove that mathematics is consistent using mathematics, essentially. It's really quite horrible. Some of the stuff Gödel proved was very disturbing, but it does seem to be right. I think what you have to do is you choose the set of axioms you want to work with, and you do say the following things follow from those. We're going to work from this, and the following things follow, and then I think you're okay, relatively speaking. It doesn't mean that you can feel safe, but at least you can be reasonably secure in what you're doing.
How about
Yes.
FIP without,
Sorry?
FIP without axiom of choice?
So what's this? Finite intersection property?
Yeah.
So I guess I'm not quite sure what you mean. I mean, the finite intersection property is a property of a collection of sets, isn't it?
Oh,
Do you mean Tikhonov's theorem?
yeah. Right.
Okay, so if you assume Tikhonov's theorem, you see Tikhonov's theorem doesn't imply the non-emptiness of the product, because an empty product would be compact. So if it so happened that an infinite product of non-empty sets was usually empty or something like that, that wouldn't contradict Tikhonov's theorem, because that product of compact spaces would still be compact. So you can't deduce the axiom of choice from Tikhonov's theorem, because it could be that you're dealing with a lot of empty spaces. I'm not the expert on this, I really must say, but I have been warned that Tikhonov's theorem does not imply the axiom of choice, and I think that's why. There are some unusual combinations of things that, when combined, imply the axiom of choice. I can't remember what it is. It's Tikhonov's theorem and something else is equivalent to the axiom of choice, but I've forgotten what that something else is. I once thought it was the non-emptiness of products, but that's directly equivalent to the axiom of choice, so it can't be that. Let's not get too hung up on all of this. We'll use Zorn's lemma occasionally in the module. I'll tell you to what extent you can get around it if you don't want to use it, but it will come in. It comes in when we do it comes in when we do Tikhonov's theorem. It comes in when we do the Hahn-Banach theorem. It comes in if you want maximal ideals in algebras. The existence of maximal ideals uses Zorn's lemma as well. A very quick application of Zorn's lemma without it. As far as I know, I don't know, again, the set theory of logic. If you lose the axiom of choice, under which circumstances can you prove that you do have maximal ideals in algebras? I don't know. No, Nottingham, okay. Yeah, sure. I guess that's right. Let me just try and remember how that works. So, okay, so then you've got some nice machinery to help you. Okay. But otherwise, if you take just some random ring algebra and it's got an identity and you want to know, are there any maximal ideals? And you've got no machinery to help you.
You could do polynomial rank with infinitely many variables.
Pol-
Are there any?
Yeah, so does that have any maximal ideals? Well, it does by Zorn's lemma. Do you need Zorn's lemma, or you'll need something, surely?
I guess you would. I don't know.
Okay, so this was the polynomials in infinitely many variables. Always have to try to remember that comments from the audience don't normally get picked up by my little microphone. So it helps if I repeat the comments. So we reckon Noetherian algebras are okay, and you probably don't need the active choice for that. But for general horrible algebras, you're going to need something if you want to get maximal ideals. Right. Gosh, we're nearly through the whole session. So here, let me give you, as a little exercise to think about, an easy application of Zorn's lemma, which is not on the sheet, to prove a result that's not obvious. Let U be a non-empty open subset of the complex plane and prove that you can find a maximal collection S of elements of U so that no pair of elements of U, no pair of elements of S have distance less than 1 apart. Now, you may be able to give an explicit collection, but let me make it slightly harder. I don't. Why have I called it curly S? I think I could. Why don't we just say? Why don't we just say a maximal subset S of U? That would be even better, I think. That's slightly easier. It's the same thing. Maximal with respect to set inclusion. And no pair of elements of this set S should have distance less than 1 apart. Well, you may be able to come up with an explicit, you may, I'm not sure, I haven't thought about this, be able to come up with an explicit way to choose such a collection. But now, just to make it slightly harder, you have some set X contained in U so that no pair of elements of S. At this time, we don't assume it's maximal to start with. So that no pair of elements of X have distance less than 1 apart. Prove that X is a subset of some maximal such set S, or some such maximal set S. So if you did manage to find some sort of way of doing this with a regular grid of some sort that maybe might have worked, this can mess you up because maybe you've chosen a few bad ones to start with that aren't in any sort of nice regular grid. But even so, you can still complete this out to some sort of maximal set. Now, if you think about what U could look like, this could be quite a tricky one to think about, but Zorn's lemma will prove this for you in about 2 lines. It just won't tell you anything about what the set looks like, just that there are some. So have a think about that one, and let me know if you have difficulty proving that with Zorn's lemma. Because that's a typical thing that is easy to prove with Zorn's lemma, and you get absolutely no information about what set you get out of it. All you get is existence, that there is one. So that means that you can choose some collection of a set of these points, and you know, it didn't really have to be an open set. I've just tried to make it something which you can intuitively think about. You won't need to use the fact that U is open to prove this result. It could have been any non-empty set, it would still have worked. I just wanted you to think about it as a nice set, so that you might be able to think about nice ways of trying to do it. Any questions just before we finish? Okay, so next time we'll get back to infinite products and Tikhonov's theorem, and we'll be using Zorn's lemma to prove that there are maximal FIP collections, which is the sort of thing you were mentioning. These things that turn out to be the same things as ultrafilters, though the way I define them is not the standard way of defining ultrafilters, but they come out to be the same thing. Okay, so that'll be next time. Let's stop there.